Okay, but work done with the gas in the different thermodynamic processes. The first process what we are doing is isochoric process, the process in which volume of the gas remains constant. So from the first law of thermodynamics flow, dq is equals to dw. If volume remains constant, work done by this one will become how much for me? 0. So work done is becoming 0, then dq will be equal to your internal energy du. That means q will be equal to your F by 2 into N into R into your delta T. So this is your Q. Q is equals to your F by 2 NR into your D. F is your degrees of freedom, N is your number of moles, R is your gas constant, universal gas constant, and delta T is your temperature difference. For monatomic gas, if I am writing, for monatomic gas, Q value will be equal to how much better? 3 by 2 NR into your delta T. For your diatomic gas, Q will be equal to your 5 by 2 NR into your delta T. Is that clear, beta? In isochoric process, volume remains constant. From the first law of thermodynamics, dq is equals to du plus dw. So dq is equals to du, q is equals to F by 2 NR into delta T. For monatomic gas, number of degrees of freedom is 3, so 3 by 2 nRT. For diatomic gas, it is Q is equals to 5 by 2 NR into your delta T. Okay, sure. Next one is isobaric process. Isobaric process means the process in which pressure remains constant. Pressure remains constant in this one. So how do you calculate the work done in this one, beta? Work done will be equal to integral of your P into your dV. Limits will be V initial to your V final. That is equals to integral P will be out. This is integral of dV. This will be initial volume and this will be your final volume. So that will be equal to your P into your V final minus of V initial. Or else I can write this one as P into your delta V. This is my equation number 1. So from ideal gas equation, I can write from ideal gas equation, PV is equals to nRT. So it is P into delta V is equals to NR into your T final minus of T initial. That is your NR into your delta T. This is my equation number 2. So I can write from first law of thermodynamics, dq will be equal to du plus dw. du is equal to how much, beta? F by 2 nr into your delta t or dt you can write. Plus dw will be equal to how much, beta? P into delta v. So it is P into your delta v. Clear? So P into your delta. P into delta V can be written as of your NR into your delta T. So this is your dq. So dq is equals to your F by 2 NR into delta T plus P into your delta V. That means I can still simplify this one. dq will be equal to your this one is F by 2 NR into your dt plus PV is equals to NR into your dt. So that is equals to NR into dt will be common. This will become for me F by 2 plus 1. So dq will become for me, this will become for me F plus of your 2 divided by 2 into your NR into your dt. So this is your dq. dq is equals to your F plus 2 divided by 2 into NR into your dt. So this will be the Q. Clear, beta? dq is equals to F plus 2 divided by 2 into NR into your dt. That is over your isobaric process. See once again. So for an isobaric process, pressure remains constant. So when pressure is remain constant, I can calculate the work done for that one. So work done by the gas will be integral of P into dV. So it is P integral of dV initial volume to final volume. So it is P into V final minus V initial, P into delta V. So from ideal gas equation, PV is equals to NR into T. So P into delta V is equals to NR into T final minus T initial. That is equals to NR into your delta T. From first law of thermodynamics, dQ is equals to du plus dW. So dQ is equals to F by 2 NR into delta T plus P into your delta V. Okay, so dQ is equals to F by 2 NR into dt plus NR into dt. So NR into dt is common, F by 2 plus 1. dQ is equals to F plus 2 divided by 2 into NR into dt. This will be dQ in terms of degrees of freedom. For monoatomic, diatomic, triatomic, you can write the value of F and get the answer for that. Okay, so next one is third process, isothermal process. Isothermal process, the process in which temperature remains constant. Your temperature is remaining constant for this one. So when temperature is remaining constant, I can calculate the work done by this relation better. Work done by this gas will be equal to integral into P into dV. From ideal gas equation, P can be written as of your NR into T divided by V into your dV. Limits will be from V initial to your V final. So that is equals to NR into your T, integral of 1 by V into your dV. So this will be V initial to your V final. Okay, so you know this formula beta, integral of 1 by x into dx will be equal to how much beta? Ln x, or we can write this one as of your log e into your x. So I can write this one, work done is equals to NR into T. This will be ln of your V final divided by V initial. So work done is equals to NR into your T ln of your V final divided by V initial, as PV is equals to nRT. nRT is your constant. So I can write here PV is equals to your constant. So I can write here P initial, V initial is equals to your P final, V final, isn't it? So therefore, I can write from this one, V final divided by V initial is equals to P initial divided by P final. So therefore, work done will be equal to NR into T ln of your, this will become for me P initial divided by your P final. So work done is equals to your nRT ln of your P initial divided by P final. Clear? Then what will be the internal energy beta? Internal energy will be equal to du is equals to your F by 2 NR into delta T. Here delta T is how much for me? 0. There is no change in the temperature. Initial and final temperature is 0. So internal energy for isothermal process will be equal to your 0. That means from first law of thermodynamics, float, I can write dQ is equals to du plus dW. du is becoming 0, so dQ will be equal to your dW. So dQ will be equal to your dW. Clear? And in this one, very important points, I'm not doing the derivations of this one. You need to directly remember this one. For isothermal bulk modulus, isothermal bulk modulus, isothermal bulk modulus, K is equals to pressure. Isothermal bulk modulus is equals to your pressure. The same way, isothermal compressibility. Isothermal compressibility means C is equals to reciprocal of your therm. It will be equal to your 1 by P. Okay. K is equals to your P, I can write dP by dV will be equal to your tan theta, anything that is fine for this. These are two important formulas you need to remember in the isothermal process. Clear, beta? Next one. Polytrophic process. So for your polytrophic process, PV to the power of x will be equal to constant. PV to the power of some x is equals to your constant. Okay. So for this one, work done will be equal to 1 divided by 1 minus whatever x you are taking, that x into your, this will be your P final, V final minus P initial, V initial. Clear? Clear, better? For polytrophic process, PV to the power of x is equals to constant. Work done is calculated with the formula W is equals to 1 by 1 minus x, P final minus V final, P final, V final minus P initial into your V initial. Or else I can write this one as W is equals to your PV is equals to nRT. So it is your N into your R divided by 1 minus of your x in terms of temperature. If I'm writing T final minus of your T initial. So this will be the work done direct relation. Very important for the NEET examination. For the polytrophic process, PV to the power of your some x will be equal to your constant. Clear? Isothermal is over. Polytrophic is over. Now let us try to go for the next one. Fifth one. This one is fourth one. Adiabatic process. What do you mean adiabatic process, beta? There is no heat transfer in this one. No heat transfer. Isn't it? So in adiabatic process, there is no heat transfer. That means dq will be equal to 0. Apply the first law of thermodynamics. From first law of thermodynamics, dq is equals to du plus dw. dq is becoming 0. That means I can write from this one, work done will be equal to minus of your du. That means work done will be equal to minus n into Cv into your dt. So this is your work done for your adiabatic process. Or else I can even write W is equals to minus of your N, Cv is equals to R into delta T, this one, divided by gamma minus 1. Or that is equals to your, first will simplify, work done is equals to NR into delta T divided by, if I'm removing this minus sign, this will become for me 1 minus of gamma. So this is your work done. Gamma is known as what, beta? Ratio of specific heats, that is Cp divided by Cv. And we also know this relation, Cp minus Cv is equals to your R. So Cp will be equal to your R plus Cv. So obviously Cp is always greater than of your Cv. Or else work done can also be written in terms of pressure and volume. So P is equals to P final, V final minus P initial, V initial divided by 1 minus of your gamma. So this is your W. Clear? So in adiabatic process, there is no heat transfer. So dq will become for me almost 0. From first law of thermodynamics, delta Q is 0. So delta U plus delta W will be equal to 0. That means work done will be equal to minus of du. So it is minus of internal energy is N into Cv into delta T. Cv will be equal to how much, beta? Cv is equals to R by gamma minus 1. And Cp is equals to gamma into R divided by gamma minus 1. So Cv value is substituted here, R by gamma minus 1. If I am removing this minus sign, 1 minus gamma. So PV is equals to nRT. So nR into delta T can be written as P final, V final minus P initial, V final. So work done is equals to P final minus P initial V initial divided by 1 minus gamma. Okay. So for any adiabatic process, for adiabatic process, PV to the power of gamma is equals to your constant. Done better? See. So for adiabatic process, PV to the power of gamma is equals to constant. So if I write this one in different forms better. See this. P is equals to NR into your T divided by your V. This one is V to the power of gamma is equals to some constant. So I can write here T V to the power of gamma divided by V is equals to total constant divided by N into R. So V, if it is going up, this will become for me T V to the power of gamma minus 1 is equals to your constant. So this is one relation between the TV. So I got it from ideal gas equation. So TV to the power of gamma minus 1 is equals to constant. I can even get one more relation better. So in the place of your gamma, if I'm writing, this one is a P into your, in the place of V, I can write as of your NR into T divided by your P to the power of your gamma is equals to your constant. So this one is a P e to the power of gamma divided by your P to the power of gamma is equals to your constant. So that will be equal to P, you take it one side, so it is P 1 minus gamma e to the power of gamma is equals to your constant. This is the relation between T and P. Clear, madam? Let me give you one example. If pressure is directly proportional to T power 3 for an adiabatic process. For an adiabatic process. So find gamma is equals to how much? So PV to the power of gamma kabati. So this one is P is equals to K T to the power of 3. Or P divided by T power 3 is equals to constant. Or P T to the power of minus 3 is equals to constant. Okay. So what is our relation beta? As we have P and T relation, what is there? P 1 minus gamma T power gamma is equals to your constant. That is nothing but K. So I can transfer the powers. So it is a P to the power of 1 minus gamma is equals to K divided by T power gamma. So transfer the power. Transfer the power of P. So this will become for me P is equals to some constant K divided by T power. This is gamma divided by 1 minus gamma. That means P is equals to some constant K. This one will become for me T. This will become for me how much beta? Gamma into this one will become for me gamma minus 1. Okay. So that means this will become for me PT. This one is right now for me gamma divided by 1 minus gamma, or else I can directly take this one here only. Why I'm writing a number of times. I can directly write this one here itself. So you just transfer this power here right now. So I got this answer. So this will be your P T power gamma divided by 1 minus gamma is equals to constant. So now compare this one with this part of relation beta. Compare with this one. P is P, T is this one. So we'll be getting gamma divided by 1 minus gamma is equals to minus 3. So it is gamma is equals to minus 3 into 1 minus gamma. So that will be equal to minus 3 plus 3 times of gamma. And this one is also your gamma. So if I simplify this one, all the gamma terms you take on one side and simplify it, we'll get gamma is equals to 3 by 2. So that is the value of gamma. Got it? Clear, beta? Very important point beta here. Write the next page. Okay. Sure. Keep this slope beta. Slope of isothermal, that is dP by dV is equals to minus of P by V. Please mute yourself better. The same way, slope of adiabatic, slope of your adiabatic, that is dP by your dV is equals to gamma times of your P by V. Okay, so therefore if I'm writing the relation between them, so dP by dV of your adiabatic is equals to minus of gamma dP by dV of isothermal. So slope of adiabatic is equals to minus of gamma times of slope of your isothermal. Clear? Sure. Next one. See this graph better. This is your pressure versus your volume graph. And if I give these two graphs something like this, okay, and ask you to identify which is isothermal and which is adiabatic. So what you do is simply keep a cross mark here and move in your clockwise direction. Whichever comes first, that will represent me the adiabatic. So what you do is keep a cross mark at point of intersection, at point of intersection, okay, at point of intersection, and move in clockwise. Move in clockwise. Whichever comes first, it will be isothermal. it will be your isothermal. That means here 1 is isothermal and 2 is adiabatic. Okay, like if I give you one more example. If the graph is going something like this, okay, this is 1 and this is 2, same pressure and volume. Okay, but so keep a cross mark here and grow in the clockwise. So 1 will represent me isothermal and 2 will represent me adiabatic. Clear, madam? Is that clear? So try this question, madam. Half mole of an ideal monoatomic gas is heated at constant pressure of 1 atmosphere from 20 degrees centigrade to 90 degrees centigrade. Work done by gas is close to dash. Capital R value, you take it as 8.31 joule per mole Kelvin. So, Rajan. Done. Anyone? Half moles, no beta. Number of moles are equal to how much beta? N is equals to 0.5. And temperature difference is from where beta? 70 degrees centigrade. Difference 90 minus 20. So work done will be equal to your pressure into change in volume. So delta T is your T final minus T initial beta. That is 90 minus 20. That is your 70 degrees centigrade. So that can be written as of your NR into your delta T. So N is 0.5, R value is 8.31 into 70 approximately. So just simplify it, you will get the answer as 291 joules. 291 joules. Done.